In 1876, the German experimental psychologist Gustav Theodor Fechner did a study with a group of people with no artistic experience. He showed them a number of different rectangles and asked them to choose which was the most pleasing of these rectangles. The vast majority chose one rectangle in particular, the golden rectangle. The geometric proportion, known as the golden section, has for centuries been regarded as a key to the mysteries of art, and so universal in its application, not only in art, but also in nature, that it has at times been treated with religious veneration. Based on a Euclidean theory, the Roman architect and engineer Vitruvius dealt neatly with the problem. He formulated the following rule: to obtain an aesthetically pleasing, unequal division of any given space, the lesser part must be in the same proportion to the greater, as the greater is to the whole. So to have an understanding of how the golden section works and how we can use it practically, we have to go back and do some basic high school mathematics, geometry, etc. that we all did and probably have forgotten. I'll start with actually how to draw or create a golden section rectangle. You begin by drawing a square. Now, I'm not using rulers and right angles and things all correctly here today. I'm just going to do it by hand, but you could do this with compasses and things with equipment as well. You find the halfway point of one side of the rectangle, of the square. And if you have a compass, you put your compass point here, and then the drawing point up on this diagonal corner up here. So, diagonally opposite. It could be this one as well, too. Then draw an arc down from that point. You then extend this line out, and where it hits that arc, at a right angle, draw a line directly up. Then extend this side of the square out, and you'll have created this other rectangle here off the side of the square. What you've now created overall is something that we call the golden section rectangle. Interestingly, what's also been created, as I said, is this second rectangle here. And this rectangle here is also a golden section rectangle. It has the same proportions, so the proportion of this short side to its long side, as what this to this has. If we square that rectangle out, and of course, having done this just by hand, it's not precise. Please remember that. I will create another rectangle, and this again would be a golden section rectangle and have the same proportion of one side to its other as this one did and this one did. And you can continue doing that, squaring these out like that, and it continues and goes on and on, creating these golden section rectangles that interlock and tessellate. The other thing that we observe in nature and that has a relationship to the golden section is the golden spiral. And the golden spiral, we can get that when we have our little diagram drawn up like this, by again taking our compass and drawing arcs diagonally across the squares. like that. And we create the golden spiral that we see so often in nature, most notably in things like shells. So in a shell, like the Nautilus, excuse its broken side there, oh there we go, turn it around that way so that's the right way. So the classic is that you see one of those chopped in half and you really see the spiral, but even this one in its completeness, you can still see that spiral starting to happen, and imagine where that spiral ends and how it's replicated here in my little diagram. When we now practically, you're not going to necessarily always have compasses and rulers and set squares and things to be measuring and working out perfect golden section rectangles. So it's where another element of, and this is the sequence of numbers. So again, we're going back into our maths that we did in high school, and that you may remember the mathematician Fibonacci. He came up with a sequence of numbers, and the sequence of numbers, he did a study of how many rabbits would be born over, I think it was in a 12-month period. If he started with 2 rabbits, and how many rabbits would he have at the end of 12 months? And having recorded that number, he ended up realizing and finding this sequence of numbers, which was 1, 1, there's our 2 rabbits. You start with 1 rabbit, you get a second rabbit. 2, 3, 5, 8, 13, 21, 34, 55, 89, and 144. And that would continue on. That goes on for infinity. What you're seeing here is if you take 1 and add the next number, 1, you'll get this number, number 2. If you add 1 and 2 together, you get 3. If you add 2 and 3 together, you get 5. 3 and 5 together, you get 8. 5 and 8 together, 13, etc., etc., etc. The ratio between these numbers, so our ratio between 2 and 3, 8 and 13, 34 and 55, is the same ratio that we have here that's demonstrated by the golden section rectangle, the ratio of this side to this side. And that ratio is 1 to 1.618 infinity. It's a big long number that goes on and on and on. So that's our ratio number. Now there's 2 ways that we can learn and work with that. The simplest I'm going to show you is by coming here and looking at this, back at this sequence of numbers. Now you've probably already been introduced to an aspect of the golden section by that that rule called the rule of thirds, putting things on where 2 parts and 1 part meet. It's like within our camera viewfinders, they have a 2 like this within the viewfinder and helping you compose a photograph. And this is about the rule of thirds. Now the rule of thirds is about the golden section. How do we know that? If we come back here to the Fibonacci sequence, there's the rule of thirds there. 3 parts divided into 1 and 2 has that relationship of 1 to 1.618, or roughly that relationship. The thing about the Fibonacci sequence of numbers here, though, is as you get further and further down this end of the scale, it gets further and further away from this proportion. It's actually not until you get up to about here does it get close to this actual proportion and exactedness. But when we're dealing with big numbers like this, it gets a little bit difficult to sort of work. So some 3 numbers in this sequence are a series of numbers that are relatively easy to work with, and that's the 3, 5, 8. If you take, and that so is that little bit closer to this. So take for instance, if I draw a line like this, and this is why I think using these numbers is a little bit easier also than using the rule of thirds, is that when you have a line like that and you try to divide it into 3 equal parts, it's sort of a little bit difficult. But to divide something into 8 equal parts is quite easy because you're only constantly looking for the halfway point. So there's the halfway point of that line, and the halfway point again of each of those. So now we've got 4 equal parts. And if we divide those into halves again, just by I, we've now got 1, 2, 3, 4, 5, 6, 7, 8 equal parts. And that I know where 3 and 5 meet. 1, 2, 3, 4, 5, 1, 2, 3. So it's that point there is roughly the golden point on that line. It's where the balance on that line is approximately equal to 1 to 1.618 infinity. The other way that you can be using these numbers is that if you take any given number, so for instance 9, and times that by 0.618, you will then get the golden ratio to that line, or to that size. So I haven't got a calculator. Yes, I do. There it is. So if I get a calculator, because these are sums that I can't do, 9 times 0.618 equals 5.56. So if I was to draw a 9 centimetre line, and then I would add on to it 5.5 centimetres roughly, that would be the golden section point, like that. So when it comes to then us looking and observing and then using it in art, I like you to use these numbers here. Looking at a space, dividing it into 8 equal parts, looking for where the 5 and 3 meet, and looking for what signal, placing something significant or looking for something significant on that point.